In this video, I'll be explaining membrane potential versus time graph. This is a typical graph that shows what happens when a nerve impulse is initiated in a resting neuron. So we're talking about from the time the neuron's at rest, it gets stimulated above its threshold, it sends an impulse, and then it reestablishes resting membrane potential so it can do this all over again. So in this graph entitled membrane potential versus time, we've got membrane potential on the vertical axis, the y-axis. What membrane potential refers to, potential is just a measurement of voltage, okay? The volts that can be measured across a membrane from the inside to the outside. So this graph is going to represent what's going on inside a neuron. Now, when a neuron is at rest, it has a negative charge on the inside. So at rest, we've got a line that looks like that. It's negative on the inside, below zero here. The reason it's negative on the inside is that we've got a surplus of sodium ions on the outside and potassium ions on the inside, and that, among other things, there's negative proteins and things like that inside the cell. It creates a negative environment inside the cell and a positive environment outside the cell. When a neuron is stimulated to its threshold, whatever that threshold happens to be, it will then reverse its charge and become positive on the inside, negative on the outside. Then it will work to reestablish itself and recover back to where it began in the first place. So this is what the shape of the graph looks like. What I would like to explain is what's going on in terms of what's going on inside the cell, what's going on in the membrane of the cell at various stages on this graph. So let's take a look at what we refer to as resting membrane potential. Resting potential. During resting potential, it's kind of a curious word here because the cell is not actively sending a nerve impulse, but it's far from at rest. It is actually using up ATP to furiously pump sodium out of the cell and potassium into the cell. And to keep the sodium out and to keep the potassium in, the sodium gates, I'll represent those as Na positive, those gates are going to be closed. They're going to be closed so that any sodium that gets pumped out does not leak back in. Now, potassium gates at this point, I'll call those K positive, potassium gates, well, they could be closed or open at this point. It depends on the particular gate. For the most part, they are closed. But even if a few were open, it wouldn't be a big deal because the electrical charge of negative inside the cell would tend to keep those positive ions attracted to the interior of the cell. They wouldn't leak out even if the gates were open. Most of the gates are closed, some could be open. Now, when we stimulate a neuron above the threshold, how you stimulate a neuron depends on what the neuron is. If you prick your finger, a neuron could be depolarized by physically being, the membrane physically being bumped by the pin. It could be a flash of light in your eyeball, and that could cause a neuron to reach its threshold. But there's some sort of stimulus that causes the neuron to reach its threshold, and what will happen then is that the sodium gates sequentially will open. And if it's above the threshold, lots of those sodium gates will open. Yes, I should write that. Sodium gates open. Now, when the sodium gates open, we see a dramatic change in the interior of the cell. It goes from resting membrane potential down here that's negative to what we would refer to as action potential, where the inside of the cell is positive. And the reason for that is that sodium ions will flood into the cell. They don't just sort of leak into the cell by diffusion slowly. When we open those gates, the sodium will diffuse through, but it's also going to be attracted by the negative charges inside. So sodium is going to have two forces pulling it inside, diffusion, because there's more of it outside than inside, so it will diffuse in, but also the negative charge inside attracting that sodium in. So we go from resting potential to action potential by opening the sodium gates. Now, once the sodium gates have opened, well, that's the nerve impulse, that's the impulse that's been generated, and that will trigger the next set of sodium gates to open, and the next, and the next, and the nerve impulse will propagate down the length of the neuron. In the meantime, at this particular location on the neuron, we have to reestablish resting potential so this neuron can send another impulse if necessary within just a few milliseconds. So we have to cause that charge to go back down. To do that, we have to repolarize the neuron. Now, the term repolarize comes from the fact that resting membrane potential is known as a polarized neuron. It's polarized. Polar means having opposites. The inside is opposite to the outside, negative inside, positive outside. During action potential, we refer to this as a depolarized membrane. This portion of the membrane has become depolarized. It's the opposite of polarized. It's positive on the inside, negative on the outside. Well, what has to happen is the neuron has to repolarize. It has to go back to the way it was in the first place. And to repolarize, the neuron will have to close the sodium gates, because we don't want any more sodium leaking into the cell. So sodium gates will close. But that alone is not going to be enough to repolarize the neuron. All that will do is stabilize it at the depolarized potential. So to get it back to normal, well, we have to put sodium out and the potassium in. Currently, right now, we've got both sodium and potassium in. Now, we can't just force that sodium out, because sodium can only move out using an ATP if potassium moves in. But the potassium is already in. So we have to allow the potassium to get out, which is why during repolarization, the potassium gates will now open. The opening of the potassium gates here will allow potassium to flood out of the cell. Now, before I said that, well, potassium's not really going anywhere back in resting potential, well, that's because there was a negative charge inside the cell holding it in. There's no longer a negative charge inside the cell. It's now positive inside the cell once the neuron is depolarized. Therefore, the outside relative to the inside is negative, and that will attract the potassium if the potassium was able to move through the membrane. So by opening the gates, the potassium is now able to flood out of the cell. It will move very much like sodium did in an opposite direction, though. It will move because of diffusion. It's a high concentration inside the cell and a low concentration out, and also the electrical charge. It will be attracted to the outside of the cell because the outside is negative and the inside is positive. So both of those factors will cause the potassium to rush out of the cell. And when potassium rushes out of the cell, we can see it here in the diagram. We can see this rapid change back to a polarized state. So the repolarization is the potassium gates opening. Now, it will overshoot slightly. When it overshoots slightly, we have a term for this. We call this portion of the graph hyperpolarized, because it's a little bit more polarized than it needs to be. But all of this can be sorted out just by waiting for the sodium-potassium pump to get back to business, to get back to work. Because now we've got sodium inside, we've got potassium outside. The pump can now pump in a 3-to-2 ratio, pumping 3 sodiums out for every potassium back in. And it's during this part of the graph right here where those sodium-potassium pumps fueled by ATP are going to restore the polarized state of the neuron, and we end up back at resting potential all over again. Now, there's a lot going on this particular spot on the membrane of a neuron, and this is all happening in a matter of just a few milliseconds. This happens very quickly. The neuron goes from resting membrane potential, polarized, to action potential, depolarized, then it repolarizes and ends up back at resting membrane potential all over again, all by just sequentially opening the potassium gates and the sodium gates at the right time. So let's take a look at some exam questions. All right, so very familiar graph right here. It says stimulation of a sensory neuron produces an action potential. All right, here's our action potential right here. An abnormal pattern in this action potential can be used to detect MS, that's multiple sclerosis, in its early stages. The graph below illustrates membrane potential of a normal neuron after stimulation. So this question isn't really about MS, because this is a normal graph. I presume the graph would look a little different if the person had MS. I'm just going to scroll a little bit so you can see the rest of it there. All right, so the question reads, what is the resting membrane potential for this neuron expressed to 2 digits? So resting membrane potential is going to be when the sodium channels are closed and when the potassium channels are closed, and when those pumps, the sodium-potassium pump is pumping in a 3-to-2 ratio. So that would be represented by this portion of the graph and by this portion of the graph right here. So reading it on the graph, it looks like it's exactly between negative 80 and negative 100 millivolts. So I think we could be safe to say that negative 90 millivolts would fit there. And what we're being asked for here is the absolute value. So we don't have to worry about whether it's negative or positive. That's probably just because of the form that this exam uses to enter the answer. It should be negative, but because it says absolute value, we can just put 90. Keeping in mind it's negative 90. Now, the other part we want is the maximum membrane potential during depolarization. Well, depolarization is right here. So depolarization, that is in line with plus 40 millivolts. Again, absolute value plus 40, we just write 40. So 9040 would be enough to answer this question. So that one is pretty straightforward. We can just read it off the graph, provided we are able to spot where is resting potential and where is action potential. So something tells me there's going to be some follow-up questions to this because that question was just a little too easy. So let's see what the follow-up questions are. Okay, follow-up question. Which of the following types of ion movement across the membrane would cause action potential to change during the interval from 0.2 to 0.4 milliseconds? 0.2 to 0.4 milliseconds. So we want to know what is moving across the membrane at that time. So let's go back to our graph and let's look at 0.2 to 0.4 milliseconds. So 0.2 to 0.4 milliseconds corresponds to that portion of the graph. So at that portion of the graph, what we said earlier is that the sodium gates are open. Potassium gates, well, they could be open or closed, depending. Most of them are closed. Some could be open, but again, it's not relevant because the potassium is not going anywhere anyway. But the sodium can certainly go somewhere. The sodium now is able to go through the membrane. Well, if we remember at resting membrane potential, the sodium was inside. The sodium was outside. Let's get that straight. The sodium was outside and the potassium was inside. When we open the gates, the sodium will be attracted to the negative interior of the cell. It will also have a higher concentration outside than inside, and both of those forces will push the sodium into the cell. So we're looking for an answer that says that sodium is going to move in. So let's take a look at the answers we have. Sodium ions moving into the axon. Well, there's our A right there. That's our first one. Let's look at B, though. Sodium ions moving out of the axon. That's the opposite to what we said. Potassium ions moving in and potassium ions moving out. Again, the potassium has no force to cause it to move anywhere because the negative charges will tend to keep it inside the cell. So the best answer we have here is A, sodium ions moving into the axon. All right, there is yet one more follow-up question here. On the graph, from 0.5 milliseconds to 1.0 milliseconds represents the neurons what? So let's take a look at the graph from 0.5 to 1 millisecond. So let's clean up this graph a little bit. All right, so we want from 0.5 to 1 millisecond. So we're looking at this right here, which we said was repolarization. And repolarization was when the sodium channels, the sodium gates closed, and the potassium gates open. That allows the potassium to escape the cell, and it's the potassium leaving that causes it to go from positive here to negative here on the interior of the cell. So we're looking at something that says something about repolarization, sodium gates being closed, potassium gates being open. So let's take a look at our available answers here. So on the graph from 0.5 to 1 millisecond represents. Now, there's a term here that we haven't discussed yet. Guess I should have. Refractory period. The refractory period is the time in which a neuron is unable to depolarize because it's in the process of repolarization. So repolarization is the refractory period. So it looks like A is going to be our answer because that's when repolarization occurs. Refractory period is not when there's minimum depolarization. Minimum depolarization, I'm not even sure what that phrase means because minimum polarization would, I don't know, it's an odd combination of phrases. They kind of contradict each other. It's certainly not the threshold period. The threshold would be the time in which the neuron is just reaching its minimum to be able to depolarize completely. So the word we're looking for there is refractory period. That's one of the vocabulary words you just have to get from your textbook.